All right, people, welcome back. So today we've got a lot to discuss here. So we're going to get started. Um, Today we are talking first about parametric surfaces and then about how to do the sort of analog of a line integral over a parametric surface. So first, let's recall, what is a parametric curve in space, alias a space curve? This is just a function that takes the real line, or maybe some interval within the real line, into space, right? So we normally wrote it more explicitly as the domain variable we called t, and then the outputs we called as three separate scalar valued functions, x of t, y of t, and z of t, right? And, if our domain was just restricted to just say an interval from a to b, this might look something like the curves that we've been seeing before. Maybe this is just some generic one that we've drawn here. This one's drawn to sort of start at this point and move sort of behind the z-axis there, and then maybe come around to this point over here. Okay? And so really we can think of this as just some maybe copy of an interval from the real line, or maybe the whole real line itself, that's just been kind of thrown into space in some way that is dictated by the function little r, right? So we've just kind of situated it in there in some funny way, according to how our function r says that things have to sit down in terms of x of t, y of t, and z of t. Okay, so a parametric surface in space is the same thing, except instead of being a copy of an interval inside of space, it's maybe a patch of, say, two-dimensional coordinate space placed into space. So maybe one that we could think of is this is a function now, little r, taking the plane or maybe some two-dimensional subset of the plane into space. Okay? And so we'll write this one. The domain variable we'll call u and v, one for what would be proverbially the x-axis and one that would be the y-axis over here. We'll call them u and v. And then the outputs we'll call x, y, and z, and each of those will be functions of now two variables. So we'll have little r of u comma v will have three components in its output. The first one will be a scalar valued function x of uv, the second y of uv, and the third z of uv. Okay, so let's say that u varies between a and b, and v varies between c and d. Then our domain of the surface, parametric surface, would be a little rectangle over here in the uv plane. Then this kind of generically could look like that the function r takes this little patch of coordinate space over here in the uv plane and maps it into xyz space by, maybe contorting that little rectangle around, but still giving us some kind of two-dimensional, what I would call a sheety thing, right, in three-dimensional space. And so we might call that surface itself S, just like we normally called a curve something like by C, right? So, okay, so right, and so the sort of way you might kind of talk about this is you might call little r the particular parametrization, but S just whatever this sort of image is the surface itself. Okay, so let's see a couple of examples here. So the first one, I'm going to let little r of uv be u in the first component, v in the second component, and u squared plus v squared in the third component. Now I think we can figure out what this is supposed to be. So if x of uv is just u, and y of uv is just v, then we could really probably just replace u with x itself and y with v itself, right? It's saying we know x equals u and y equals v in this context. So really, we might even just replace this so it's something that's a little bit more familiar to us just in terms of its lettering. So we could write it as the set of all x squared plus y squared in space. So all points whose x coordinate and y coordinate are given, and then the z coordinate is x squared plus y squared. Well, we know this. This is just the graph of the equation z equals to x squared plus y squared. And that is a elliptic paraboloid, right? So we've seen this many times. Notice this is the graph of a function. We have x and y free to vary however they like, and then z equals to this function of x and y. Okay, so that actually leads into a sort of general example of parametric surfaces that will be good for us to have on hand, as many of the surfaces that we've met this semester and sort of called important are themselves the graph of some two-variable function in three-dimensional space. So if f of xy is a scalar valued function of two variables, then of course, as we've seen before, the graph z equals to f of xy will be a surface in space, and we can make the following generalization to parameterize such a surface every single time. So we can always choose to parameterize with the function r of uv equals to u in the first component, v in the second component, and then f of uv, just replacing x with u and y with v. And really that replacing x with u and y with v is almost kind of superfluous in this case. If x and y play the same role in three-dimensional space that they would in the sort of plane that's mapping to three-dimensional space, then you can just really forget any other auxiliary dummy variables like u and v and just write this parameterization more plainly like you see it as just little r of xy equals to x in the first component, y in the second component, and f of xy in the third. So either of these are a valid parameterization, and in fact they're equivalent. Sometimes I do think it's nice to have to write the UV one because it's easier to distinguish that the domain of the parameterization is two-dimensional space, and it's technically not supposed to be the same as the two-dimensional subspace of three-dimensional space that's over here. There will be some reason later that you might like to write it as UV every single time. But for now, we're just kind of calling it like we see it and trying to get used to this new concept. So know that you can also do this kind of replacement in this specific instance if you like. Okay, so now let's do a different example that's not the graph of a function of x and y. So let's consider the cylinder in space, which is satisfied by the equation x squared plus y squared equals to 1. Right, so this is like the unit circle in the xy plane, but then z is allowed to vary and be any number that we want. So it's that unit circle just stretched upwards forever and downwards forever in the z direction. So this surface looks like it has some nice rotational symmetry about the z-axis. And so we might like to call upon what we know from cylindrical coordinates. Right? This cylinder actually has a very nice equation in cylindrical coordinates. So maybe let's call on that. So in cylindrical coordinates, r theta z, this surface has equation given by just r equals to 1. Right? This is the set of all points in space written with cylindrical coordinates where the radius is equal to 1. This means then that we can take the cylindrical coordinate transformation that says x equals r cosine theta, y equals r sine theta, and z equals z, and translate this guy into x, y, and z that way. So we'll have, in particular, that x equals to 1 cosine theta, since r equals 1 is the equation of this cylinder. Y equals to 1 sine theta, since r equals 1 is the equation of this cylinder. And then z still equals z, right? It's free to be anything we want. So now our two free variables that are floating around are theta and z. And so we can use those two variables to now parameterize this surface as little r of theta comma z equals to cosine of theta in the first component, that's x, sine of theta in the second component, that's y, and z in the third component because that's z. Okay, so this is fun. So I want to do one more example like this with, obviously, my favorite surface, the sphere, right? So let's consider the sphere that satisfies the equation x squared plus y squared plus z squared equals to 1. This is a sphere of radius 1, centered at the origin. And I think, as we've seen now in this course, the best coordinate system to describe this sphere is spherical coordinates, right? In spherical coordinates, this sphere has a very nice equation, namely rho equals to 1. So then if rho equals to 1 in spherical coordinates, then theta and phi are free to vary about as they, I think theta varies from 0 to 2 pi, and phi varies from 0 to pi, right? So now that theta and phi are the sort of free variables left to roam around in this particular sphere here, we can use those to parameterize this sphere as a two-dimensional object, really, because rho equals to 1. So we'll remember the spherical coordinate transformation, right? That x equals to rho sine of phi cosine of theta, and y equals to rho sine of phi sine of theta, and z equals to rho cosine of phi. So putting all those together with rho equals to 1 gives us that x equals to sine of phi cosine of theta, y equals to sine of phi sine of theta, and z equals to cosine of theta. So then using just theta and phi, now we can parameterize this sphere. And I forgot to note on the slides here that theta will go between 0 and 2 pi, and phi will go between 0 and pi. All right, so I think that's all we've got for an introduction to parametric surfaces. But I think these 3 examples, and along with the sort of general one that came first, are probably the best examples that you're going to need going forward in this course. So we can talk about these more at length in office hours or in class time as well. So stick around for the next part of this talk, where we'll talk about how to do some interesting integrals over surfaces inside of space. So we will see you then.